Okay, so this is lecture 4 on manometers. So we talked about pressure measurement in the last class, and manometers are a method of measuring pressure that's used. Like the images show here, a classic manometer that gets used a lot is what we call a U-tube manometer, and this is named aptly because it's in the shape of the letter U. And typically these are elongated tubing that are filled with a fluid. Nowadays, a lot of times it's an oil or water that's had a dye added to it. In the past, you would also see ones with mercury inside of them. So for the one image, we got one where it's an example of a U-tube manometer from Dwyer. On there, you can see sort of a yellowish color. That's a dye that gets added to the water to just help show it show up better on the manometer measuring scale. The other example here is from an example problem in the book where, again, they've got mercury as their measuring fluid, and then it's measuring the pressure in some water piping and displaying that pressure, or you would calculate that pressure given the heights of the water and the mercury. So when you go to solve a manometer type problem, when we write out the equation, what we typically want to do is start at one of the endpoints in the manometer, either the open end or the closed end, or if it's two closed ends, just pick one end or the other, and then start working from there in terms of writing out your equations. If one end is open, it's generally easier to start your equation from that end. So you pick the open end and then work your way around to the other end of the manometer. And what we do is using our relationship of our change in pressure is equal to our specific weight times height, or delta P is equal to gamma times H. We can write out our equation in terms of the expressions of pressure for each of our different heights of fluid that we have. One thing we want to make sure of, though, is we want to make sure we use the correct algebraic symbol for each value that we put in, because on this manometer, we're going to have fluids on both sides, and the pressure on one side of the manometer is going to counteract the pressure on the opposite side of the manometer. When we'll work our way then around from the open end to the closed end, and when we get to that final point, we'll equate all of those expressions that we've written to that pressure at the final point. Once we've done that, we can then substitute in our known values and then solve for our desired pressure. So for our first example, we want to use that same example that was on the first slide, where we've got a U-tube manometer that's connected to some water piping, and it displays that we've got some mercury as our measuring fluid, and then we've got a height of water here on this side where the water is coming out of that tap into our piping at point A. We've got, and it's pushing down onto the mercury and then making the mercury rise up on the other side. So in our examples, or in our pattern, we said we wanted to start with the open end and then work our way around to the closed end on these open manometers. So if that's the case, I want to write it out in terms of my expressions of my pressure. So for the mercury on the open side, I'm going to say that my specific weight of my mercury, gamma sub Hg, is going times my height of the mercury, so H sub Hg, and I'm using Hg here because that's the periodic abbreviation for mercury. So like on a periodic table from chemistry class, Hg is your symbol for mercury. So on the right-hand side of the column, that's the only measuring fluid that we've got is just the mercury. We've got air, but it's open to atmosphere, so we're going to have zero pressure there. At this point here where the mercury is at the same level on both sides, the two pressures cancel each other out. So that's going to be our equal pressure line. And so we can ignore anything that's below that line, and really we're just concerned with the things that are above the line. Because again, remember our rules that we said that anything that's at the same point in a system is going to have the same pressure on both sides. So our pressure across that equal pressure line is going to be equal on both sides. So really we can just move over to the other side. And now we want to account for the water. So the water is going to act in the opposite direction. The pressure of the water is acting downwards in this manometer, whereas the mercury is acting downwards on the other side. And so these two pressures are counteracting each other, where they're opposing each other around this bottom and canceling each other out. So we're going to write it out as our specific weight of our water times the height of our water. And then we said we want to equate it then to our final point, which at our final point, we're going to have some pressure P sub A. So I'm going to say that it's equal to my pressure P sub A. So that's my equation for the problem. And so now I know my specific gravity of mercury, I know the specific weight of water, and I can determine the heights of both sides. So I should be ready to solve the problem. I'm going to write it out. I always like writing it out to where I write what I'm solving for on the left-hand side of my equation. So I'm just going to, basically just flip the equation. No signs or anything are going to change, but just rather than having the PA at the end, I'm going to say that PA is equal to, and then for my specific weight of the mercury, I've got 13.54 times my 9.81 kilonewtons per meter cubed, and then times the height of my mercury, which is going to be 0.25 meters, and then minus the specific weight of my water, which is going to be again, 9.81 times the height of my water, which on this, it's going to be the 0.015 plus the 0.025. So I've got 0.4 meters. If I then solve that for my mercury piece, I'm just going to do the 13.54 times 9.81 times 0.25, and I get that that's equal to 33.21 kilonewtons per meter cubed, or meter squared, excuse me. So it's kilonewtons per meter squared. The meters are going to cancel out the cube sign, and we're just going to have kilonewtons per meter squared. And then minus 9.81 times 0.4 is going to be 3.92. kilonewtons per meter cubed. So now or per meter squared. So now if I solve, I should get that it's going to be 29.29. And that's kilonewtons per meter squared, or what we more typically write out is it's going to be kPa, or kilopascals. So 29.29 kPa would be our final answer, and that's going to be our pressure at A. So that's how we would solve an open-ended manometer, and that's a pretty common one that we would use where we're just trying to solve for the pressure at a specific point in a system. Commonly, we'll see that a lot in like HVAC equipment where we just want to measure what's the pressure at a point in a piece of ductwork or through a unit. But sometimes we also want to know what's the pressure differential between 2 points, but not actually the actual pressure of either one. And so for that, we can use a differential manometer, which is going to be tapped into two sides of a system and will help us display what is the pressure differential between those 2 points. So in this one, we want to set up our equation, or we want to calculate for the pressure differential between 2 points, point A and point B, and we want to get our final answer expressed in the terms of PB minus PA. So we want to get it into the difference between the pressure at B minus the pressure at A. So if we write that out, again, we want to start at one end or the other. So for this one, I'm going to start at point A, So if I start at point A, I'm going to have some pressure at A, piece of A, and that's going to then also include on that side, I'm going to have my pressure due to my height of my oil. So I'm going to say plus gamma sub O times HO. There's two different pieces of, or two different legs of oil in this one, so I'm going to call this HO1. And that's going to be all that's acting on this one before I get down to my equal pressure line down at the bottom between points 1 and 2. And then on the other side, I'm going to have some water, so that's going to be counteracting my oil. So I'm going to say minus the gamma of water times the height of that water. And then minus the specific weight of my oil. Again, I've got some oil up here in the second leg that I want to account for. So I'm going to say minus gamma oil times times the height of the oil in the second leg. So I'm calling it HO2. And then that all is going to be equal to my pressure at B. So if I rewrite this equation, I can take the PA over to the other side, and I should get that PB minus PA is going to be equal to, and I'm going to do some combinations here. I've got HO1 and I've got HO2, so I'm going to say that it's going to be equal to the gamma of the oil times, and it's going to be HO1 minus HO2. And then also subtracted from that, I'm going to have my gamma of my water times the height of my water. So I get the equation in the form I want it to be in, and now I can start plugging in and solving because I know the gamma of my oil, or I can calculate it using the specific gravity at 0.86. And then I also know my specific weight of my water. So by using those, I can calculate everything that I need. So if I plug in my gamma of my oil, I'm going to have the 0.86 times 62.4. That's going to be pounds per cubic foot. And then times, so in this oil, I'm going to have 33.75 inches on one side. I've got the 29.5 plus that 4.25 up above to get that full height along this side, all the way up to my center line through A. So it's going to be 33.75 minus 4.25. And then we want to divide by 12 inches per foot. And then from that, I want to subtract, I want to count for my water, so I got 62.4 times, I have my 29.5 inches divided by, again, 12 inches per foot. So I set up the equation 0.86 times 62.4 times 33.75 minus 4.25 divided by 12. And then I've got minus the 62.4 times 29.5 inches divided by the 12 inches per foot. So if I continue to solve, I should get PA or PB minus PA is equal to, for the first piece, should get 131.92. That's going to be pounds per square foot is going to be the units, and then minus 153.4 pounds per square foot. And so if we solve, we should get that it's negative 21.48 pounds per feet squared. But again, more commonly, we want to get our final answer in PSI. So what I'm going to do is I want to multiply by 1 over 144 square inches per foot squared. And I should get for PV minus PA, we should get that it's equal to a negative 0.15 PSI. So in terms of pounds per square inch, pretty small value, but so only 0.15 PSI difference between the two sides. But again, that greater pressure in A is pushing the water up into the leg that's on the same side as the pressure at B, which would indicate that the pressure at A is greater than the pressure at B, and so a negative answer is what we would expect it to be. This is another closed manometer with two connections on the B side and the A side. And this one's measuring the pressure differential between water and oil and using mercury as a fluid. But I want to hold off on this problem until Friday, and we'll do this one together as a class just so we can answer any questions that people might have as we work through one of these problems. So save the space on your note sheet, and we'll cover this one on Friday, but we'll move forward onto the other slides. So in the industry, there's more than just YouTube type manometers that we may use. There's also well type manometers, and these are manometers that where we have a well of fluid, and then the fluid goes into a tube that then goes up on a scale that we can measure a rise in pressure along a scale, do it by applying a pressure to that reservoir. So by a small change inside the reservoir, we can produce a larger change on our scale, and we can see the height. So this one is another image of a well type manometer from Dwyer, and then it's got a graduated scale on it that would then read off what is the pressure for that well type manometer. Incline manometers are another popular style. These ones are a lot more sensitive due to the nature of the incline. So for a small change in height, they can show a large change along that leg and allow us for a lot finer measurement on the manometer. So when I was in graduate school, this was the type of manometer that I would use for doing some pressure loss measurements along ductwork. So typically on this one, you can see it's even set up to where the scale on it automatically reads out in inches of water, and there's no additional calculations that need to be used. So for some of these manometers, they'll have scales that are already calibrated for the measurements that they're going to be making. On other manometers, if we just had any general scale and we were measuring a height or wanted to figure out what that height is, we could use the equation where the height is equal to the length of change L on the manometer times the sine of the angle for that slope, so the sine of the angle theta. Barometers are another type of pressure measuring device. Again, these ones will measure absolute pressure and not just gauge pressure, because remember, a barometer is going to measure atmospheric pressure. And so what this one does, the classic manometer that or barometer that used mercury would have been a tube that was filled with mercury, and then it gets submerged into a well of mercury that's open to atmosphere. And as atmospheric pressure changes, it will cause the mercury in that vacuum tube to move up and down. And this would then allow us to express that pressure. And it was very common, and still is common, to express barometric pressure in the form of either inches of mercury or millimeters of mercury. So if we wanted to calculate the atmospheric pressure on one of these manometers, given the height of the mercury, H, we could just express it as that, or again, we could apply the specific weight of mercury and calculate our pressure using that specific weight of mercury. Some of your dial gauge type manometers that are measuring pressure, or what we would just call a pressure gauge, might use what's called a burden tube type of manometer. And so this is one where a pressure change will cause pressure to act on the burden tube, which then causes a movement in linkage, and that linkage will then move a gear that then moves our indicator pin on our dial and will represent the pressure that we're seeing inside the device that we're measuring that pressure with. Another one is a magnehelic type gauge. You see these a lot on different air handling units and HVAC equipment. And for this one, it moves the pin not like the burden tube does with the linkage, but on this one, it moves a magnet either closer to or further away from a coil that's then attached to the indicator pin. And what happens is, as that magnet moves, the magnetic field changes, and it causes that spiral to rotate, and then causes the indicator pin to move and display the pressure for the device. So as I mentioned with the barometer, it's very common to express pressure in terms of a column of liquid. So you'll hear, like with HVAC ductwork, we might talk about how many inches of water pressure the ductwork has, or for something like a barometer, you might hear us say how many inches of mercury or millimeters of mercury is the atmospheric pressure at. And so that's another common way to express pressure. But again, we can still use that height to also calculate what is an actual pressure in PSI or Pascal. So for any of those, if we wanted to convert it over into units that we could use, like into the form of PSI or KPA, again, we would still use that exact same equation that we've used before of our specific weight gamma times our height would be equal to our pressure. We also have the conversion tables in the back of the book in Appendix K that we can use, and those would give us our pressure conversions as well. You can find conversions for inches of water over to pascals or PSI in the back of the book, and you should also be able to find conversions for inches of mercury and I believe millimeters of mercury over into pascals and PSI. So in this example, we ask what is 1 inch of water pressure equal to in PSI and pascals. So there's a couple different ways we can go about solving this. If we wanted to solve using our classic equation of P is equal to gamma times H, we could use the specific weight of the water and use the 62.4 pounds per foot cubed, and then multiply by 1 inch, divide by 12 inches per foot. We could use that and calculate and get an answer in PSF, and then go on and convert to PSI, and then eventually over to pascals. Or we can use Appendix K and if I go to Appendix K, I can look it up and see that 1 inch of water is equal to 249.1 pascals. So that would be the value of what 1 inch of water is equal to in pascals. Or I can also see that it says that 27.68 inches of water is equal to 1 psi. So if I want to get it into inches of water, 1 inch of water is going to be equal to 1 over 27.68 psi. Or if I do the math, I'll find that it's 0.036 psi. So a very small amount of pressure is what 1 inch of water is equal to. So when we're talking about air movement in ductworks, it doesn't take a lot of pressure to move that air through the ductwork and to supply it out to spaces. So for homework, I'll have 5 problems to do, 3, 6, or chapter 3 problems 63, 65, 71, 83, and 86. A couple of these are manometer type problems, and then other ones are some barometer and incline manometer type problems. So fairly straightforward, but again, we'll go through that one last example problem on Friday in class, and this homework will be due on Monday. So that should be Monday, September 9th. So hope everyone has a good weekend, or not a good weekend, but I hope you had a good holiday weekend. And again, sorry for not having class tomorrow, but I'm getting that will take replaced. And we'll see you in class and lab on Friday.